In the last lecture, we covered special relativity and general relativity. It went into a little bit of depth about special relativity. I said that the first postulate of special relativity is that the laws of physics are universal, meaning they're the same for all observers in uniform motion relative to one another. Now let's cover the second postulate of special relativity. The second postulate of special relativity states that the speed of light in a vacuum is the same for all observers, regardless of their relative motion, that is, the motion of one observer relative to the other, or relative to the motion of the light source. Let's think about this. This might not seem like a big deal, but actually it poses a rather strange intellectual predicament. Let's consider an observer here, moving at, let's say, 1 meter per second. Not so fast. But let's say we have another observer just below him who's moving at 10 to the 7th meters per second. The relative velocity of observer 2 relative to observer 1 is quite large. Now let's say we have a beam of light passing by them both. The speed of light happens to be 3 times 10 to the 8th meters per second. According to the notion of relative velocity, which we covered in the previous lecture, we might expect that this observer would see the light traveling at a slower speed than this observer, because observer 2 is moving very quickly in the direction that the light beam is traveling. However, the second postulate states that this isn't true. Both observers see the light traveling at the same speed. How is this possible? So why relativity? It seems like relativity is pretty strange, and it must have been difficult for Einstein to think of. Well, relativity was created as a response to strangeness that was observed in classical Newtonian mechanics, which is what we've been studying, when the extremes of the mass and size scale were approached. In various experiments, it was demonstrated that classical mechanics fails on the atomic level, say in the domain of quantum mechanics, which is what special relativity covers, and also it was shown to fail on the largest of the mass and time scales. So let's say on the level of astronomy. This is the domain of general relativity. Experimental data has shown that the postulates of special relativity are relevant. These experiments showed that while Newtonian mechanics suffices at more typical sizes and masses, relativity is necessary and much more accurate at very large and very small scales. A particularly interesting case is the black hole because it is at once very massive and very tiny in size. Black holes don't clearly fall in the domain of either general relativity or special relativity.